Thank you very much. It's always a great pleasure to be here at the GGI, so thank you very much for the invitation. Uh, in my talk, I would like to review some of the results that we have obtained in the last couple of years in our group in Torino, together with Marco Billo and Maria Luisa Frau, and our young collaborators, Alessandro Pini, who is now in Berlin, Francesco Galvagno, now in Queen Mary in London, and our PhD student Paolo Vallarino in various combinations. What we did was to study a certain class of n equals 2 superconformal gauge theories in 4 dimensions and try to analyze some observables in these theories with the aim of obtaining exact results, namely results that are valid for all values of the coupling constant. I think that all of us agree that perturbation theory is the perfect tool to analyze an interacting quantum field theory. But if we really want to understand an interacting quantum field theory, sooner or later we have to explore the strong coupling regime, where certainly perturbation theory cannot be used. So in general, working at strong coupling is difficult, but if the theory enjoys a large amount of symmetry, then remarkable progress can be made. And this is the case, for example, of n equals 4 super Young-Mills theory. As we also heard in the talk by Arkady yesterday, enjoys a lot of symmetry, and thanks to these symmetries, one can obtain exact results. Specifically in the large n bit, not only in the planar approximation, but also in the subleading corrections. And let me briefly review, just to set the stage, what we know in n equals 4 super Young-Mills. We all know that it is a conformal theory at a quantum level. It is a theory which has an holographic dual, and in some sense it can be regarded as the simplest gauge theory in 4 dimensions with a field content of spin up to 1. If we discuss n equals 4 super Young-Mills in terms of n equals 2 content, we have a vector multiplet which contains the gauge boson a mu and a scalar complex scalar phi plus fermions, and an hypermultiplet which contains 2 extra complex scalars plus fermions, and all of these fields are in the adjoint representation. I will focus on operators and observables which are built with the fields of the vector multiplet, even though it is also interesting to consider observables and operators which are formed with a hypermultiplet. The simplest operator that you can have in this theory are the chiral primary operators, which are simply gauge invariant combination of the scalar field phi. So, for example, trace phi to the k at point x is an operator which I can call a of x. This is a BPS, it's protected. It has conformal dimension k, and you can study, for example, the correlation functions of these operators. Another important example that we saw yesterday is the Wilson loop, the BPS Wilson loop, which is 1n for normalization, trace of the path ordered exponential of the usual expression on a circle C, a mu, x mu, but because of supersymmetry, you need also a combination with the scalar fields in order for this to be supersymmetric. And also, with this operator, you can study, for example, its expectation value or the the correlation function of local operators and line operators, and so on and so forth. And what we know, for example, by focusing on these local operators. Next week, Marco Billo will mainly talk about Wilson loops. So today I will talk about local operators. What is known is that we can compute the correlation functions. For example, the two-point function of these operators, OK and O bar K of Y. O bar is simply the complex conjugate, so that we can saturate the charge. This two-point function is fixed by conformal invariance. The space-time dependence has to be this. And the only thing that is left is the normalization in the numerator, which I may call GK, which is a function of the number of colors and of the coupling constant. Similarly, I can compute the three-point function of K, L, Y, or bar P of Z. Again, conformal invariance fixes the structure of this three-point function to be something like this: x minus z to the power 2k, y minus z to the power 2l, and here there is a coefficient which depends on these numbers, k, l, p, which is a non-trivial function of the coupling constant and the number of colors. Of course, in order to saturate the charge, P has to be equal to K plus L, but that's inside this. So these are numbers, or actually functions, of n, the number of colors. I'm using a gauge group SUN, and of the gauge coupling. Of course, these functions depend on how you normalize your operators. So in order to get rid of this ambiguity, you introduce what people call the structure constant, so the normalized three-point function KLP, which are nothing but these coefficient GKLP divided by the product of the two-point function under square root GLGP. In this way, you get rid of the normalization of the operators. And it turns out that if you compute this object in the large n limit and go into infinity, these structure constants are, first of all, very simple. Yes? But these operators cannot contract because they are chiral. So phi can only contract with phi bar. The propagator is a phi with phi bar. So these are this is an example of what are called extremal correlators, in which there is a U1 charge. So this carries a U1 charge, and so this is a positive. This is positive. This has to be negative. But two positives it's because O cannot contract with O, but only with O bar. Because these are scalar fields, complex scalar fields. I mean, this is the standard form of the usual 3-point function in which you simply cannot contract. Sorry? Yes. This has dimension k, this is dimension L, this has dimension P, and P has to be equal to k plus L because of conservation. Because, as I told you before, this O bar has to soak up the charge of this O and L. So these structure constants, first of all, in this limit are very simple, but they are independent of the coupling. So, and the result is something like this, K, L, P, with that restriction, divided by N. And this is for all values of the coupling. Since I'm working in the large N limit, I will introduce the 't Hooft coupling, G Young-Mills square times N, and this is the coupling. So this is independent of the coupling. So this is the result which works both at weak coupling and at strong coupling. This was obtained long ago by Lee, Mingwalla, Rangamani, and Seiberg in the early days of the ADS-CFT correspondence. Clearly, at weak coupling, you can compute these structure constants using a diagrammatic approach by computing Feynman diagrams. And in the opposite regime, at strong coupling, you can compute it using ADS correspondence, and the two results match. This is the first, the simplest example of an exact result. Maybe it's sort of trivial, so to say, because it's a constant, but nevertheless, it's something which holds for all values of lambda. Another example that we saw yesterday in Arkadi's talk is the vacuum excitation value of the Wilson loop. If we compute the vacuum excitation value of the Wilson loop in this theory, and we take the large N limit, the leading order, the planar contribution, is again can be given an exact formula in terms of the Bessel function. It's like this. By this I mean that's the leading planar term. There are subleading 1/n corrections. Also for those, you can write exact expression. Actually, you can write in terms of Laguerre polynomial, as we saw yesterday, the expression at finite n. This is another example in which you have a result which is valid at all values of the coupling constant. If you expand this in the limit lambda going to 0 from the Bessel function, you obtain 1 plus lambda over 8 plus lambda squared. The coefficient is something, 192, I think. Etc. And you can reproduce this expansion diagrammatically using Feynman diagrams, as people did. On the other hand, the same function can be expanded at strong coupling, and you obtain a completely different expression. You have e to the root lambda over lambda to the 3/4, if I remember correctly. Yeah, let me write it as root 2 pi, and then there is the leading term 2 lambda to the 3/4, plus there are corrections which are suppressed inverse powers of lambda, etc. Yeah, in this case, yeah. But I mean, you can compute it more easily by looking at the planar contribution. Yes, so this is what we have in n equals 4, which is the simplest gauge theory. And in this theory, there are a lot of other exact results, like the ones that I have simply highlighted here, for other observable, for other correlation functions, for the Bremsstrahlung function, the cusp anomalous dimension. I mean, there is a long list of other examples in which you can find exact results, in the sense that you have formulas which are valid for all values of lambda, and therefore you can test them either at weak coupling with perturbative methods or at strong coupling using holography. What we did was to generalize this construction for theories which are not maximally supersymmetric. So for theories which have n equals 2 supersymmetry, which are less constrained than n equals 4, but still have a sufficient amount of symmetry that may allow for such treatment. And today I would like to discuss with you some calculations that we did in this n equals 2 conformal field theory in 4 dimensions. And I consider the simplest example that is obtained from n equals 4 by an orbifold projection. So these theories are generically quiver theories. The gauge group is a product of factors SUN. You may have many of them. In principle, m factors of SUN. And you have a matter content in, which is quite simple, namely bifundamental hypermultiplets. So you can draw diagrams like this for each factor of SUN. You draw a dot, and then you have a circular quiver like this, where these arrows means hypermultiplet, which is fundamental for this and anti-fundamental for that gauge group. Just to make things as simple as possible, I will discuss just the case in which the orbifold group is a Z2, so we have just 2 factors of SUN. So we have 2 nodes of SUN, and we have a matter in the bifundamental representation like this. So this is the gauge group, this is the matter content. This theory, you can check, is conformal in both nodes. You compute the beta function coefficient and identically vanishes. So it's conformal at the quantum level. It is, in some sense, the next to simplest theory after n equals 4 super Young-Mills, in the sense that it has a reduced amount of supersymmetry, but still can be obtained from n equals 4 by a simple projection. It enjoys in principle, you can have a different coupling constant, but it's much easier to consider the symmetric orbifold in which G1 and G2 are the same, and that is the choice I make, even though the techniques can be applied also in the asymmetric case, even though we have not yet concluded the calculation in the general case. So. This theory has a nice realization in string theory, in type 2B string theory, in terms of branes. You can start from a stack of 2n D3 branes in type 2B theory, and you divide these 2n branes into two groups of n each, and then you, in this way, generated two SUN theories on the word volume of the two things, and the strings that go from one stack to the other, or vice versa, describe precisely this hypermultiplet. This D-brane construction is instrumental in order to obtain the holographic dual, which is also known as an orbifold, of ADS5 cross S5. So we are in the perfect situation in which we can mimic what it is done in n equals 4 Sperian-Mills, but in a less constrained setup, which is this. There are other examples that you can consider, because, for instance, you can put a further orientifold projection and identify this quiver and obtain a gauge theory with just one factor of gauge groups and different matter content, but in some sense this is the simplest case that one can consider. So massless, yeah, massless. Um, that's quite interesting, because you can give a mass to the hypermultiplets and obtain the so-called star theory, n equals 2 star theory, which are generalization of the n equals 2 star theory, which is a massive deformation of n equals 4. So, but here I consider them to be massless. Okay, so in this theory, we may introduce several types of observables, and the simplest ones are the chiral primary operators, similarly to what I had in n equals 4 super Young-Mills. The only difference is that I have two nodes, and therefore two vector multiplets. This one I label with an index I equals 0, and this one with an index I equal 1. So I will have a trace of phi 0 to the k, and a trace of phi 1 to the k. But since I am in the symmetric orbifold, the coupling constants are the same, it is more convenient to introduce the symmetric and anti-symmetric combination of these operators, which I called OK plus minus, and maybe I put a factor of root 2 to normalize. So these are the observables that I consider chiral primary operators. I call them untwisted if there is a plus sign, because they are even under the exchange of the two factors. I call them twisted if there is a minus sign, because these combinations are odd under the parity exchange that exchanges the two nodes. And then I can start my calculation, and for example, I try to compute the analog of the two-point function. So OK plus minus of x with, again, for the same reason as before, I have to take also the anti-chiral operators, O bar k plus minus of y. Clearly, because of this parity, plus only talks with plus and minus only with minus, otherwise there is a cancellation. And the conformal invariance tells me that this is again of the form that I should expect, with a coefficient here gk plus minus. And similarly for the 3-point function. So I actually could use the same formulas here. I simply put here plus, minus, plus, minus, and here I have a plus, minus. And here, for example, I have minus, minus, plus. Here, in this case, of course, I need to have an even number of untwisted operators, sorry, of twisted operators. So all of them can be plus, or two of them can be minus. So let me consider, just to make things simple, a 3-point function in which two of them are twisted and one is untwisted. And this I denote as minus, minus, plus. So the structure is as before, but now these functions are much more complicated than the ones in n equals 4 super Young-Mills. If we construct, similarly to what we have here, the structure constants, then we see something. Well, let me also consider the case in which all operators are untwisted. So all of them are pluses. Then the structure constants, when all these are untwisted, all of them are pluses, is just like in n equals 4. There is only a trivial factor of root 2 due to the normalization due to the orbifold. But again, these 3-point functions, or actually the structure constants, do not depend on the coupling. That is somehow to be expected, so to say, because the untwisted operators do not feel essentially the projection. They are the even part of the theory, so they should behave very similarly to what we saw in n equals 4. And indeed it is. Whereas if I start computing correlation functions with twisted operators, I get something which is very different. Minus, even at the first order in perturbation theory, we start seeing a deviation from n equals 4. So this is a non-trivial function of lambda. So this is an example in which, in the correlation function of chiral operators, you may have a structure which is a non-trivial dependence on the coupling constant. So how do we compute these functions? As I mentioned, one possibility is to start doing a perturbative calculation. So I take the operator, let's say the 2-point function. I take OK plus, which is 1/2 trace of phi 0 to the k plus trace of phi 1 to the k. If it is minus, here I have a minus. I take the product, OK plus minus of x, O bar k plus minus of y. I take the expectation value, so I have to make the various products, and I can clearly obtain structures which I can represent in terms of diagrams. At point x, we will have the insertion of k lines, k scalars, k of them. In point y, we'll have the antichiral fields, so we'll have again k stars. And then I have to join these two subgraphs with propagators, or with propagators and vertices that I obtain from the interaction action. So it's a standard quantum field theory calculation, but as you may easily realize, it is quite involved, because especially if you want to go high up in the perturbative expansion. So at the first perturbative order, you can do this calculation and you get some results, but clearly that is not what you should do if you want to explore higher order, even in perturbation theory, because calculation becomes very, very involved. Uh, this phi 0 with phi 1, then clearly at tree level there is no contribution because phi 0 talks only to phi 0 bar and not to phi 1 bar. But you can bring down from the interaction vertices structures, can find a contribution. Yes, they are protected in the sense that the conformal dimension remains k. But this function here is a generic function of lambda. It's not something that you can say it's constant, just combinatorial. So in order to make progress, you have to do this kind of calculations using a different method. And the method is the one of supersymmetric localization, which words translates the path integrals over fields into finite integrals over matrices. So it is much more efficient and much simpler to perform, even though the content is exactly the same. So from this point of view, it's, from a perturbative point of view, localization is just a trick to make these Feynman diagram calculations very, very efficient. And so that we can go very easily high up in perturbation theory. So let me just highlight what is the idea. We are studying a gauge theory in a flat 4-dimensional space-time, but this is a conformal theory, so we can make a conformal transformation and map the flat space-time to a sphere. Once you are on a sphere, namely on a compact space, then you can use Pestum's result about localization from 2007, and you can, following his proof, write the partition function of your gauge theory in terms of an integral over the elements of a matrix. So the partition function is a path integral over all fields, but this path integral localizes on a certain subset of configurations which are in one-to-one correspondence with the elements of a matrix, a unitary matrix, sorry, an Hermitian matrix A. Suppose for the time being that the group G is just SUN. So it's a little bit simpler than my theory, but just to illustrate the idea. So I have a matrix A, Hermitian matrix, belonging to SUN, and then the partition function of the gauge theory can be written as an integral over this matrix A. This matrix A is essentially, at least from a qualitative point of view, associated to the vacuum expectation value of the scalar field, phi, roughly speaking. There is a prefactor which depends on your normalization, and I'm here using our normalization. So 8 pi square n over lambda to n square minus 1 over 2. That's a convenient normalization. As you know, in the vacuum expectation values, these overall factors drop out. And then the integral is over a matrix model in which there is a very simple Gaussian term, e to the minus traces a square, with the standard 1 over g square, which I prefer to write in terms of lambda like this. That's the Gaussian part of the matrix model. And then there is the contribution of the fluctuations, the one-loop determinants around these localization points, which is typically written as the one-loop square, which is a function of A. And there are also non-perturbative contribution due to instantaneous corrections, which are related to the Nekrasov partition function. Since I'm studying this theory in the large and limit a la Tuft, for me this instanton contribution is because instantons are suppressed, but it's an interesting development also to study the contribution of the instanton part. So in my case, this doesn't play any role, and we have this function, and Peston tells me what is this function. And for any theory with n equals 2 supersymmetry, group G and hypermultiplets in a representation R, this Z1 loop square can be written as follows. There is a contribution coming from the fluctuations of the vector multiplet, which is in the adjoint, which can be written as this: E I different from V. U and V run from 1 to n, labels the eigenvalues of the elements of the matrix A. The function h will I specify in a moment, AU minus AV. And there is a contribution from the matter content, so the hypermultiplet in representation R, which can be written as the product over all weights of the representation R of the same function A of W of R dot A, where A is this vector whose elements are A1, A2, etc., AN, subject to the tracelessness condition because we are in SUN. And this function H is a known function which is e to minus 1 plus gamma, the Euler constant, x squared, times g of 1 plus x, ix, g1 minus ix, where g is the Barnes g function. So it's this is the result of Peston. Log of x of h of x when x is small is a simple as a simple expansion in terms of zeta functions minus 1/2 z3 x to the 4th plus 1/3 zeta 5 x to the 6th, etc., etc. So, for example, if the argument is small, then you can replace this with this expansion in zeta function. So this is to tell you that if you give me an n equals 2 theory, not even conformal, any n equals 2 theory with the gauge group G, this is written in terms of the AU of SUN, but this construction is general, and you give me the representation R of the hypermultiplets, I have a recipe to write this, this term here. Notice, for example, that if I apply this recipe to n equals 4, since the hypermultiplet are in the adjoint, this denominator has the same structure as the numerator, because hypermultiplet and vector multiplet stay in the same representation. So therefore these cancel, and for n equals 4 super Young-Mills, the matrix model is a trivial Gaussian matrix.
So when the theory is not conformal, lambda is the scale of the sphere?
Yes. Here I have set the radius of the sphere. Remember that I told you that we mapped the plane to the sphere, and I set the radius of that sphere to 1, so it doesn't appear. If the theory is conformal, then everything cancels. That's the bare coupling that remains unrenormalized. But if the theory is non-conformal, for example, if you take SQCD with a number of flavors, which is not twice the number of color, then this coupling is the renormalized coupling, and the scale R, where is the sphere. So this is to tell you that this path integral of your gauge theory is reduced to a matrix integral. You have to integrate over the elements of this matrix A. And that's the content of Pestun's paper. In our case, we have two gauge groups, so the formula is a little bit more complicated, but not much. We have two matrices, one for the first SUN and the other for the second SUN. We have two such factors. So for our quiver theory, this matrix model is this 8 pi square, this normalization factor n over lambda to n square minus 1. Then we have integral of dA0, dA1. You have two matrices. The Gaussian factor is as before, just trace of A0 square plus trace of A1 square. And then there is this one loop. The one loop is non-trivial, but it is the product over I from 0 to 1 of h, that function of AU minus AV, I. So the two vector multiplets contribute as expected independently, and then there is a contribution from the bifundamental hypermultiplet. You can work out what they are, and it is h of AU node I minus AV node I plus 1, with the understanding that this index is the cyclic with period 2. So this is the matrix model, which, according to Pestun, describes the path integral of our gauge theory. Now, first of all, you can make a rescaling of the variables so that you bring the Gaussian part with a canonical normalization, which means that you take A1 and you replace it with AI, with AI, and you absorb it lambda over 8 pi square n times AI. So in terms of the rescaled quantities, which for simplicity I name AI as before, this term goes away. But what you get here, of course, is inside this function A, precisely the root lambda 8 pi square n, because you have rescaled your A's, your matrix elements. And from the Jacobian of the measure, you get rid precisely of this factor. That's why I put it there from the beginning. Now you see that if you are a perturbative person, then you are on business because the argument of these nasty functions in terms of the Barnes G functions are with explicit lambda here. So you can expand this using this simple formula, and therefore you can write your matrix model in the following form. Z dA0, dA1, e to minus trace A0 square plus trace A1 square. And all this becomes something that you can write in the form e to the minus s int. I call it s interaction because it's a function of A which can be thought as an interaction for the matrix model. I write precisely in this form so that this I can write at e to the s int, so s int is the log of this function, and therefore I can use the expansion for the log of h, which is simple. If I do all this algebra, which is quite straightforward using this input, then I obtain that S int, this interacting matrix model, has the following form. It's 2. I write the formula because it will play a role, not the details, but the structure. It is important. So first of all, we see that the matrix model is not free. There is an interaction. So it's different from n equals 4, as we expected. But the interaction is still of a nice form because it is an expansion. Remember that I expanded this function in powers of lambda, so clearly I get a perturbative expansion. There are some coefficients that come out from working out. This function log h have the odd zeta functions. So there will be a series in each term of these is odd zeta function. So this is the coefficient. And then there is the A dependence. And the A dependence comes in this form, is a trace of A0 to the 2m minus k minus trace of A1 to the 2m minus k. So precisely the odd combination of power 2 minus k, and then trace of A0 to the k minus trace A1 to the k. So this is interacting part of the matrix model. You may say, well, you are a perturbative person because you are giving me an expansion in terms of powers of lambda. So how can you hope of obtaining exact results because this is a perturbative expansion? It's true, but this conclusion is too naive and it's too quick. And I would like to show that actually inside this structure there is a very nice resummation that is possible. So this is the partition function. Now, if we want to compute the correlators, I have to tell you what are, in the matrix model, the representatives of the gauge theory observables. In the gauge theory, we were computing correlators of traces of phi, and these were gauge fields. So what is the matrix model representative of this local operator? I told you that A, the matrix AI, is essentially related to the expectation value of phi I. So naively, you may say, well, the matrix model representative of these operators is what I have in the matrix model, trace of A 0 to the k plus or minus a trace of A1 to the k. That's the obvious guess that you would make. But it's not quite right because, as I told you in answering Andrea's question, these fields are chiral. So it means that these operators do not have self-contractions because the constituent fields cannot contract among themselves. Whereas A is an Hermitian matrix, and because of the quadratic part, there is a propagator, A with A. So this structure has self-contractions. So it cannot be the representative of this operator of the gauge theory. But if you put things in this way, then you immediately know the answer. I have to remove all self-contractions. And to remove the self-contraction means I have to normal order this operator inside the matrix theory. The normal order removes all self-contractions, and therefore now I have a candidate to identify with in matrix model to identify with the gauge theory operators. Doing this normal ordering means removing all self-contractions, or equivalently asking that this operator does not contract with all the ones with the lower dimensions, because I've removed all contract. So it is nothing but a change of basis. It's normal ordered, but I could say that this is the operator which in the matrix model corresponds to the gauge theory operator, and it is nothing but a change of basis with respect to the naive choice that you had. This change of basis can be worked out, and actually it has been worked out long ago by several people. And just to make the story short, because I'm running out of time, because I was very slow, so sorry about that. But I interpreted this more as a sort of a lecture than as a sort of a talk, so I would like to then stop me whenever you feel it's done. So this is a change of basis. So we can work out this normal ordering just as a warm-up exercise in the free theory. So let's disregard for a time being S interaction, and let's work this in the free theory. So we will have 1 over root 2 trace of A0 to the k plus or minus trace of A1 to the k, normal ordered, but in the free theory. So these operators I call, I give a name to these operators, which are P plus minus k. And if you compute the 2-point functions of these operators in the free matrix model, it's almost a triviality, because downstairs you have to put this structure here. Then you have a Gaussian term, so in the end you simply have to compute Gaussian integrals with words. And you selected the coefficients in this normal ordering, change of basis, in such a way that these operators P are orthonormal or orthogonal to each other. In the free matrix model, they are delta KL times a factor which turns out to be, if I remember correctly, n over 2 to the k. So it is perhaps more convenient to make this operator to be orthonormal. So let me remove this normalization factor and define this p with this square root of factor in such a way that they are orthonormal, sorry. This change of basis is particularly useful because now I can go back to the interaction action. Here, there was a trace of A0 to the m minus k minus trace of A1 to the m minus k. And here it was a trace A0 to the k minus trace of A1 to the k. This was the structure. Now I see that here only the odd combinations appear. So I may rewrite this interaction action in terms of these new operators. Again, it's just a change of basis, which looks strange, but it is quite rewarding if you do that, because now with this change of basis, the interacting Hamiltonian, interacting action as int becomes, here you see you have the seed, the leading term of p minus of 2m minus k. Here you have the leading term of p minus k. So you expect that S interaction is quadratic in these p operators that I have introduced there. And indeed it is. You do the calculation and you can bring this interaction action in this form. Still, it's a perturbative expansion. There is a p, k. There is, of course, some relabeling of indices that you have to perform, but that's trivial. Pk minus, pl minus. We see the structure of p coming from here and there, and of course there is the tail, and the coefficient is xkl, and xkl, I write this formula here, turns out that the result of the calculation, it's a brute force calculation at this point, but it's a series in powers of lambda. Minus 1 to the p, and then there are some coefficients, factorial squared, there are a lot of factorials that come from the Gaussian integrals, k plus l plus p factorial. There is the odd zeta functions, because I relabel indices, it becomes k plus l plus 2p minus 1 over k plus l plus 2p, and there is a power of lambda, k plus l plus 2p over 2. So you get this, and you say, well, what do I do? Well, if you start looking at these series, after a while, you maybe recognize a pattern that suggests how to resum it. First of all, you can replace the odd Riemann zeta function using an integral representation. And then all this conspires so that this xkl becomes written is the series expansion of this function xkl which is essentially a convolution of two Bessel functions of from 0 to infinity dt over t e to the t minus 1 square. That's essentially the kernel that you have to use in order to rewrite the odd Riemann zeta function in terms of an integral. And all the rest becomes a convolution of two Bessel functions whose argument depends on lambda, JL of t root lambda over 2 pi. And here there is also a prefactor, minus 8 root KL and some signs. But what is important is that this now has this expansion when lambda is small, but as it stands can be taken for all values of the coupling constant. So it's true that the matrix model comes about with an intrinsic perturbative structure, but and at least in this specific case, but actually in many other cases, it can be reduced to a sort of a convolution of Bessel functions. So the dependence on the coupling constant now is generic. So this is an infinite matrix, KL, but its dependence on lambda is exactly given by that expression. By the way, similar convolution of Bessel functions appeared in other contexts. For example, I think the first, but maybe I'm wrong, but the first example where a similar structure occurred was in the solution of the Beiser-Eden-Staudacher equation for the Caspar anomalous dimension, in which they wrote another matrix, which is a convolution of Bessel function of this type with a different kernel. It appears this same structure in the study of the so-called integrated correlators, in which you have deformation with mass parameters and you take derivatives. Again, this convolution of Bessel functions appear with different kernels. In the study of other observables, other types of form factors, correlation functions, Grisha-Korczemski and Belitsky show that also there a similar structure appears with a different kernel. So it seems that this structure is general that it seems, and it would be very nice, in my opinion, to understand the deep origin of it. But can I have 10 more minutes and then I stop? Then what we can do at this point? Well, we can compute the 2-point functions and eventually the 3-point functions, not just in the free theory, but in the interacting theory, because now the interacting theory is much simpler. It is quadratic in this. So the first thing that you may do is to compute pk plus pl plus now in the interacting theory. It means that I insert this operator in the matrix model, which is the free matrix model with the interacting part. It means that in the free theory, I have to compute the following: pk plus pl plus e to minus s int divided by the partition function of the interacting matrix model, which I can regard as a vacuum expectation value in the free theory of the interacting part. But S int depends only on P minus. It means that these operators, which are P plus, are transparent, so they can be taken out of the expectation value, and therefore, for these two-point functions of untwisted operators, even in the interacting theory, I have the same result of the free theory, because all effects of the interactions cancel between numerator and the denominator. So they remain delta KL. But of course, if we compute P minus with P minus, then we have a contribution from the interacting action, pKl minus. It's a similar formula, so it's pk minus pl minus e to the minus s interaction, evaluated in the Gaussian matrix model, divided by e to the minus s int. But s int is of the form p minus x p minus. So when I expand in powers of s int, I start having, when I take the 1, I have a delta KL as in the free theory, and then I have the contribution coming from the interaction at the first order in S int. I have a minus pk minus pl minus S int minus, which becomes plus, pk plk minus pl minus, and then S int. So I get clearly the connected two-point function in presence of S int. S int is p x p minus p minus, so I do my Wick contraction. It means that at the first order, this delta KL is corrected by, as int actually has a minus sign and factors of 2, which you have clearly to take properly into account. You contract the p with p with p, and so you get xkl. If you go to the next order, you have x squared kl plus etc. etc. So it means that for these observables, the three-level propagator, which was trivially the identity, gets corrected by the insertion of one time this matrix X, two times this matrix X, and so on. So it becomes a dressed operator, and I formally resum these as 1 plus x squared, so 1 over 1 minus x KL. So the inverse of that matrix, whose elements are that convolution. Right, yeah, of course. Of course, this is naive, but it is p squared minus x p squared. So there is 1 minus x. So it's clear that the propagator is 1 over 1 minus x. You do the same thing for the three-point function. The calculations are essentially of the same type. They are quite simple because what you have to do is to expand these formulas and then do these Gaussian integrals over the matrix P. If you do this, you can finally obtain your results. However, there is still a point. You remember that I defined the P operators, these objects, which has this simple structure in the free theory. The observables that I want are the ones in the interacting theory. So there is still one further step to perform, which is made in normal ordering in the interacting theory. But this is again another change of basis, this time dependent on on the interaction, on the coupling constant. And this can be done, and the algebra is not immediately obvious, but the result is quite simple. And I write the result, for example, for the two-point function of the true operators, OK, OK, in the matrix model, which I don't put a bar in the matrix model because I have just A, but these two-point correlators in the matrix model captures the function which sits in the numerator of the two-point correlators of the integer theory. And this thing can be, plus, this thing can be written in a compact form as follows. For example, let me suppose that these are even operators. And even, just to make well, for the plus, actually, there is nothing new with respect to n equals 4. So let me just write the interesting result. For the odd ones, these are the interesting observables because the other ones are planar equivalent to n equals 4, so we get the same thing. So take two twisted operators of even dimension, okay, which is something that you obtain. Here you have a prefactor, which is 2n, n over 2 to the 2n, and then the result of all these math can be put in this elegant form as a ratio of determinants of this matrix. Actually, it's 1 minus the determinant, it's the determinant 1 minus x. I should say with even. Even means that I consider both k and l, the elements with even. And upstairs is the determinant of the same matrix, even, in which I have deleted the first row and the first column. So this x even starts with, so x even, let me write it here. X even starts with x to 2 with the convolution of J2, x to 4, etc., x 4, 4, x 6, 6, and x even with this 1 here means the same matrix in which I deleted the first row and the first column. So it starts with 4, 4, 6, 6, 4, 6, and so on. So it's very explicit. And similarly for the others. Now, it may seem very cumbersome, but actually it's not. So let me suppose that this is the result, and now we want to check perturbation theory. We can expand this Bessel function in powers of lambda, and you easily see that the more you go down in the matrix, the higher the indices of the Bessel functions are, and therefore the expansion, the perturbative expansion starts to higher order. So it means that if you want to truncate your analysis to a given order, then you can simply restrict it to a subset of finite matrices. And in this way, no. Strong coupling is different. But let me try to show what. Okay, so no, it's not this one. Yes, yeah. So for example, this is the similar formula for O3, O3. Now you have to take x odd, namely 3, 3, 3, 5, and so on. You put the lambda expansion of the Bessel function, and very quickly, with a simple mathematical code, you can go very high in powers of lambda. So you can generate very long perturbative expansions. And the first few terms, for example, the zeta 5 lambda to the cube term, can be checked against a perturbative calculation with Feynman diagrams, and you get precisely that number. But checking already the zeta 7 and so on becomes quite complicated. Once you have this very long perturbative series, you can start asking what are their properties. And these series are convergent. They have a finite radius of convergence at lambda equals pi squared. And exactly. And if you analyze in the complex plane of lambda the structure of singularities, then you see that there is a branch cut that develops at lambda equals minus pi squared. So in the lambda plane, here is the physical value pi squared. It's the unphysical values minus pi squared. The branch cut is here, but all the singularities are outside this. It means that at lambda pi squared, nothing special should happen. So it means that you should be able to go beyond that perturbative bound. And indeed, you can take this very long series in lambda and do some numerics. For example, resum them à la Padé, for example. And therefore, you start getting expressions that can be analytically continued beyond this radius of convergence. And you start seeing that when lambda starts to increase, this function starts to go down. So they decrease with lambda. However, you can, yes. No, no, I mean, in this quiver theory, G odd and G even, the numbers are different, but the structure is the same. It's exactly the same thing. It's a peculiar feature of this matrix model in which there is an accidental cancellation in the S interaction. Yes, we did that. There is a cancellation of contributions proportional to zeta 3. That is one of the very preliminary checks that we did with Francesco Galvagno when he was a student, to check that the matrix model prediction without zeta 3 matches the field theory calculations at that order. And indeed, one has to be careful, but it... So, the same kind of singularity. So I think that this is because this theory is a descendant of n equals 4. So it's n equals 2, but it is just an orbifold of n equals 4. So probably, but I'm not... in other examples that we looked at, the same singularity occurs, but I cannot make a general statement. So actually, we can do more than this because since we know this x in terms of lambda exactly, now we can study not just the perturbative expansion of lambda, but the strong coupling expansion. And as we and Gerald, Arcadi, and Matteo Beccaria did, we studied this x KL as a function of lambda. And if you study it at, for example, you have to use the Mellin-Barnes techniques. You use the representation of products of Bessel function and then use the Mellin-Barnes approach. You see that this x odd, but the same is true for x even, when lambda goes to infinity, becomes quite simple. It is linear in lambda, when lambda is large, times a matrix S, which is just 3 diagonal. All the rest disappears. And therefore, you can, this is for x odd, but the same is true for x even. So if you are naive, when you have such a result, let me say that G3, just to use that thing, is 3n to the 8 cube, and then we have a determinant of 1 minus x odd with one column and row removed, the determinant of 1 minus x odd with all entries. If you are naive, you say when lambda is large, x is much bigger than 1, so I can delete or neglect the 1. And therefore, here I have the determinant of a matrix whose elements are linear in lambda, and here the same. But here the dimension of the matrix is smaller. So there is one row and one column less. It means that the powers of lambda that are in the numerators is one less than the one in the denominator. In other words, from this analysis, you expect that this goes like 1 over lambda. You may be not naive, you can be very analytic and do the calculation and check that this is the case. Once you have this, we have another example of an observable which we know all the way from weak coupling to strong coupling. And at large coupling, this quantity scales as 1 over lambda. And here is the numerical extrapolation, even with the Monte Carlo simulations, that with Matteo Beccaria, the Padé resummation, and the dashed line is the strong coupling extrapolation. You see when lambda increases, the agreement is marvelous, and indeed it can be proven in an analytic way. So just to summarize, Arkady, Matteo, and Grisha Korczemski went further in analyzing this strong coupling expansion of these ratios of determinant, and they worked out also the subleading corrections, which are these terms which scale with extra powers of lambda. Lambda prime is a redefinition of lambda with constant factors. So the leading term is what we have obtained, and these are the subleading corrections. The same thing can be done for the 3-point functions, and therefore we have an estimate for the structure constants. And the result of the structure constant is amazingly simple. Remember that in n equals yeah, indeed, that's very, very, very remarkable. But these structure constants KLP for these observables minus P in weak coupling, they are like the ones of n equals 4, the ones which I started from in my lecture. Just there is a factor of √2. This is when lambda goes to 0. Whereas when lambda goes to infinity, the leading term is 1 over lambda for the 2-point function, but the 3-point function also goes as 1 over lambda. So when you take the normalized structure constant, this lambda disappears, and you get something which is k minus 1, L minus 1, P over √2n. Of course, we know here also the subleading corrections. And just to summarize, these subleading corrections originate from these terms in square brackets. And these subleading corrections are quite important because now we have a quantity in the strong coupling regime, and we could check whether this is in agreement with the holographic calculation. What we did, I don't have time to discuss this, is to perform an explicit calculation of the 2 and 3 point functions using holography in this orbifold model, and extending the old result by Leeming, Waller, Angamani, and Seiberg, we managed to find a precise match with this localization result at the leading order. Notice that the further corrections scale as powers of 1 over lambda prime, and these in the supergravity or better string theory description corresponds to alpha prime corrections. So the zeta 3 lambda prime to the 3 half should correspond to a zeta 3 alpha prime cube term, and so forth for the others. So this result from localization is a very strong prediction from what should happen in the holographic dual theory beyond the leading supergravity approximation. Still in the planar limit, so 3-level approximation, but with a string correction. And indeed, Arkady and his collaborator started to try to understand the stringy origin of the first alpha prime cube zeta 3 correction that is implied by this holographic calculation. It would be very nice to have a more general picture of this. So sorry for being so long, but I wanted to try to explain the main ideas as well as some techniques. These results are quite interesting in some sense. First of all, this is a strong prediction for string theory in ADS. And at the same time, the appearance of this structure is it's not a coincidence, it's not accidental in my opinion. This 1 over lambda expansion is an asymptotic series, so it has a 0 radius of convergence. It means that this series has to be supplemented with non-perturbative, exponentially suppressed non-perturbative corrections. And therefore, the program of resurgence to study the resurgence type structure of this expansion is also, in my opinion, quite interesting. And similarly to what you and others have done for the cusp anomalous dimension, which originates from exactly the same kind of structure. So understanding the non-perturbative corrections and their role and relevance also from a holographic dual point of view would be interesting, I think. Thank you very much for your attention. I have to check, but if I'm not wrong, in this business of integrated correlators, multiple zeta values occur. But I have to check. Maybe I check the literature and I come to you with the right answer, because, yeah. 4-point functions, I mean, the matrix model cannot give a 4-point function because 4-point function is not fixed by conformal symmetry. There are these functions of the cross ratios which have to be computed. We are not detected by kinematics. The matrix model, however, for the 4-point function can give rise to an interesting information about an integrated version of the 4-point correlators. And so it's an integral over the 4-point functions with a specific measure. And this can be analyzed also using these matrix model techniques at strong coupling, even in n equals 4, where the matrix model is trivial, but in order to have these integrated correlators, you have to break n equals 4 with a mass deformation. So you go into n equals star. At that point, the matrix model of n equals 2 star is very similar to this. It has an interacting part, which is different, technically different, but in spirit is the same thing as here. And again, you bring down a convolution of Bessel functions with a different kernel. So you can reformulate everything in terms of this formalism. And also there you see you are in n equals 4, but because of this deformation, you have introduced a sort of interaction, effective interaction. And when you bring down that, then you may when you integrate with that measure, you may generate other structures. But I want to be more precise. Maybe I come to you. No, not. I can tell you that for the observable that Alberto was talking about, you do not get. However, it is possible, though nobody has done the calculation, you can consider a 6-mass derivative. Yeah. That might be a higher point function, or it might still be a 4-point function. Nobody really knows because you do a microscopic calculation. And over there, you generate a kernel which involves 6 vessels with some non-writable terms, and that might give you some data. Moreover, another development is by doing this massive deformation, not in n equals 4, but in n equals 2 theories in presence of fundamental interaction, fundamental hypermultiplets like SQCD. So, and the structure becomes much more involved, but richer. So I cannot exclude a priori at this point that these higher zeta functions occur. But I mean, one has to be very careful before making a general statement. Hmm. I don't know. This came through logic that I explained just by all the other examples that I've seen have a similar structure. The only difference is the function of t, which is here, the kernel of this. But other types of convolutions, I don't know. But for example, you probably will see next week if instead of having localized operators like this, you have extended operators like Wilson lines, then there will be more structures even with the other Bessel function, the Bessel function I, not only the J. So there will be other convolutions, but in the cases that I know, this is the structure. The only flexibility is in the kernel.
So there's another representation for fixed K and L because that's precisely what happens at the genus expansion of the integrated operators. And you can actually find
But
there's a median resummation of some.
yeah, but I mean, you may use the properties of the Bessel function to get it, or it's.
So it's a little bit complicated. In hindsight, you do, but the way we got it,
Yes, but for NL you can analyze this, okay, but in the gauge observables like the coefficients in the correlators, you don't have just a matrix element of X. You have these determinants, and this there is a beautiful analysis that Grisha, Arcadi, and yeah, because once you are for this matrix, but it's also interesting to look at the large K limit of this, the large charge limit, so to say, when in the correlators. So there are a lot of. And it's quite interesting from a diagrammatic point of view, because uh, in the planar limit, we know that we have to take, in the large n limit, the most planar diagram to get the linear. When you are in the large K limit, you have to take the least planar diagram. There is a nice interplay, and so there are the maximally non-planar diagram, perturbatively. Yeah, I'm talking about perturbative. Then I don't know what happens in the non-perturbative expansion, but that is also an interesting line of development to study the large charge limit of these correlators. So thank you very much. But I don't. Sorry. Thank you.